Okay, so just to give a really brief introduction, we have a new learn and share session today with Dario Fiore, who accepted to give a talk on his latest work, which is related to simulation extractability on different in one of the most relevant protocols that we commonly use in the zero knowledge landscape. The talk is going to be more or less oriented on giving explanations on what simulation extractability is, how does it work, how do we analyze it, and how do we basically check it for protocols. And this is where I think Dario will link it to his latest work, which you can check in the description of the video, in the invitation, or basically anywhere you want. It's in ECR and in print. So, Dario, thank you very much for attending, and whenever you want, you can start.
Yeah, thanks for the nice introduction. Yeah, so I'm Dario from India. I mean, for those who don't know me, I'm a cryptography researcher here at India Software Institute, and I work on zero knowledge in general and SNARKs, vector commitments. Okay, so I think Carlos already gave more or less, what's the outline of the talk. So I'll start by giving an introduction to security definition of non-interactive zero knowledge. So this is something very, very basic. But since I'm assuming that, maybe people here could be familiar with constructions, but maybe a bit less familiar with the formalism to define security of constructions, I will try to spend some time on this. And then I'll introduce the notion and the problem of malleability of proofs in zero knowledge, and why they're important. And then the second part of the talk will be about how can we construct this simulation extractable, also known as non-malleable zero-knowledge SNARKs. And I'll talk about our recent work. All right, also feel free to interrupt me and ask me questions interactively. All right, so what are non-interactive zero-knowledge proofs? So this is non-interactive zero-knowledge proof is a proof system for NP relations. So an NP relation, it's a relation that about pairs of a statement and witness that satisfy a certain relation. For example, it could be I don't know, X could be certain strings of 256 bits, and then in the relation we have all pairs for such that XW, such that the hash of W is X, right? That's an example. Okay, so now let's assume that right, there are these two parties, the prover and verifier, and the goal of the prover is to show that there exists a witness so that XW such that XW is in the relation. Okay. So, for example, I mean, maybe to pick something which in which sometimes the witness does not exist. Let's say that X is an integer, and you want to show that it factors in two prime numbers, and W is the two prime numbers. More formally and easy, a non-interactive zero-knowledge proof consists of three algorithms. There is a setup algorithm that, given the security parameter, produces what we call a common reference string. So think of them as a public parameters. And using this common reference string that is generated once and for all, the prover can use the statement X and the witness W to generate a proof, right? So then the verifier, simply given the statement and the proof, will say accept or not. Okay, so what is important is, and why they're called non-interactive, is that once you have generated this CRS, the prover has to send a single message to the verifier. Okay, so they don't have to interact. Now, what properties do we want from non-interactive zero-knowledge proofs? The first one is completeness. Essentially says that if everybody is honest, then the verifier accepts. So in particular, if there exists a witness for X, then when you verify a proof generated for X, the proof must pass verification. Okay, so nothing special here. Okay, then there are two more properties that formalize the security of non-interactive zero knowledge, that are zero knowledge and soundness. So let's start with zero knowledge. Okay, so in words, zero knowledge means that the verifiers learn nothing about the witness beyond the fact that the witness exists, right? So the verifier gets to know that it exists, but it doesn't know which witness you used and nothing more. Now, how is this formalizing cryptographic terms? And this is like, so pay attention to this because this is going to be relevant to understand how do we define simulation extractability. So in order to model the fact that the verifier learns nothing, we're comparing two games. So here, can you see my cursor moving?
Yeah, we can.
Okay, good. So in one game, we generate the CRS using setup, and then there is this adversary that we call D, so it's the one that has to decide, has access to an oracle. And this oracle, think of it in this game, is the oracle where it can sense a statement and a witness, and it gets back a proof generated by the proof algorithm. And then we want to compare this against the experiment where instead, the CRS is generated by another algorithm that is a simulation, simulated setup algorithm that generates the CRS together with the trapdoor. And then, like, the proofs are generated using a simulator for the prover. That is an algorithm that uses the trapdoor in order to generate the proof given only the statement, right? Now, pictorially, we can think that this guy, the verifier, submits XW, and then he doesn't know what happens inside the box. So either, it could be that the proofs are generated using the proof algorithm, or maybe it could be that the witness is like discarded and the proofs are generated using the simulator. So what we want is that this guy, the verifier, should not be able to tell these words apart. And formally, this means that if we measure the probability that he outputs 1 in the game where he plays with the simulator and the probability that he outputs 1 when he plays with the real prover, these two probabilities must be close. Okay, so I actually forgot to say that their difference must be negligible. Okay, so again, to recap, we say that an ISIC is zero knowledge if, in addition to the setup, proof, and verification algorithms, there exist two other algorithms that are sim setup and sim proof, such that these two probabilities are close to each other. Okay. Okay, any question on this? Okay, so the intuition is that if proofs can be generated without the witness, using some trapdoor, of course, then this means that and if these proofs are indistinguishable from the real ones, then it means that the real ones don't convey information on the witness. All right, so the other property is soundness, which in English terms, we could say that it means that a malicious prover cannot make a verifier accept false statements. So assume that here there is our adversary that has a statement X for which there is no witness, no witness that makes it in the relation, then it should not be able to produce a valid proof that is accepted by the verification algorithm. Well, that's it, right? So this means soundness. So in cryptographic formalism, this means that for every adversary that is probabilistic polynomial time, so it's bounded in time resources, it cannot come up with a statement and a proof that is valid and for which there is no witness. So here it's important that the CRS is honestly generated for these two, for this property to hold. Okay, so now an important observation at this point is that for some relations, soundness is not sufficient as a condition. Okay, why? Because think of a relation for which there exists always a witness. So essentially, every X could be in R, or let's say for every X there could be a W in R. An example is, let's say that the relation is checking SHA-256 preimages. Maybe with overwhelming probability an X as a preimage. So in that case, soundness is not sufficient as a notion, right? So what we actually want is a stronger notion that is called knowledge soundness, that actually says that if the prover is successful in convincing the verifier, then she actually must know the witness W for that statement. And in cryptographic terms, this is formalized by saying that if the adversary managed to create a proof that convinces the verifier, then there exists an extractor that can output the witness W, such that the W is a good witness for X. Now, in the more precisely, the definition is models the opposite. The probability that the opposite happens more precisely means that we say that an ISIC has knowledge soundness if for every adversary A, there exists an extractor such that, when we look at the experiment where the adversary produces statement and proof and the extractor outputs the witness, then we want that there is negligible probability that verification outputs 1, and the witness is a bad one, right? It's not a witness for X. Okay, so to recap here, the message about knowledge soundness is that if you manage to create a proof that is accepted, then the intuition is that you should know the witness. Now, let's see what happens when you use an ISIC in the wild, right? So in real systems. So what happens is that an adversary that normally in knowledge soundness is supposed to receive the CRS and produce a statement and a proof, in the real world may actually happen that she has seen several proofs generated by other people. Right, so there could be other provers that she can have access to that are producing statements and proofs. Now, let's say that we are in this environment. Now, what's the guarantee that if this adversary produces a valid proof, she really knows the witness for this proof? So we cannot be convinced about this because, for example, a trivial thing that the adversary can do is to just copy-paste one of these statements and proofs that she has seen, right? So, and that's unavoidable, right? So we cannot prevent this. What we could do, however, is to say, okay, look, maybe this we have to accept this fact, and we can have a definition that says, look, if you are in this, let's say, distributed environment, then when you return a proof, I will check that this is not a proof that you have seen. Okay, for now, I'm staying high level, all right? The problem is that perhaps, like seeing a proof for one of these X1, X2, X3 could help the adversary to create a proof for a new statement X. And this is what is called a malleability attack. So, for example, to think about example, let's say that you have seen a proof about X, maybe X is some it's the result of a computation, and then you have another proof for, let's say you have a proof for X1 and a proof for X2, and this allows you to create a proof for X1 plus X2, right? It's actually something that, in some proof system, it is possible. And that's what we call a malleability attack. So in contrast, what we would like is, in some sense, is non-malleability, that informally we can say that it's the guarantee that copy-pasting is the proof is the best possible attack that you can do. So let's now see how this concept is formalized in, I
have one question.
Yeah.
When you say we haven't seen this proof before, who has the bookkeeping of all of the proofs that have been seen so far?
Good question. So we're going to see this in this slide, but essentially it means that we will define an experiment where we actually bookkeep what the adversary asks.
Makes sense.
Okay, so right. So to model simulation soundness or simulation extractability, the idea is that first of all, like the adversary has access to a CRS, and this CRS is generated by the simulator algorithm. Okay, and then the adversary can ask proofs on statements of her choice, right? So, and she can do this as much as she wants. But here the point is that these proofs are generated using the simulator and the trapter. So this models the fact that the adversary is seeing proofs for which she may not know the witness, right? Because she may even ask, for example, false statements here. Now, after this process is over, the goal of the adversary is to come up with a new statement X star and a proof pi star. And we are going to check that this is valid, so it passes verification, but also that the pair X star pi star is not in the set of pairs that have been like asked and received from the oracle. Okay, so that's exactly the bookkeeping. So it means that, you know, if more formally we would accumulate all xi pi I in some set, and you check that X star pi star is not in this set. Now, again, we want to model extractability. So we want to model knowledge soundness. So to do this, what we essentially the idea is the same. So we are assuming that we look. So we require that for every adversary A that plays in this game, there exists an extractor that, you know, given the view of A, I mean, here I'm not using the full formulas because it would be a bit more complicated, but think about that the extractor has access to every input of A, including the transcript of the queries that she has made. Then this extractor will have output a witness, W star, and then again, we check that the statement X star and proof pi star pass verification, that they are a new pair, and that like the witness that was extracted is a bad one, right? So we, in this case, we say that the adversary and the extractor win, and we want to, what we want is that the probability that this happens is negligible. All right, so this is essentially the definition of of simulation extractability. Right, I want to mention that there is also a weaker version of this definition in which instead of checking that the pair X star pi star is new, we may be enough with the fact that only the statement is new. So in this model, for example, could be useful to model schemes where proofs are re-randomizable. So in that case, it's kind of easy to obtain a new proof for the same statement. But weak simulation extractability models the fact that you cannot do better than this. Okay, so if you have a question on definition, this could be a good moment.
I have
otherwise, I'll move on.
Can you hear me?
Yes.
Okay. I have a question in regards to this weak simulation extractability concept that you mentioned. What's the exact trade-off that it brings if we analyze, I don't know, Plonk or whatever proving system based on simulation extractability or weak simulation extractability? What can we say about it depending on which way we analyze it?
But you mean what kind of trade-off? Do you mean a trade-off in terms of security or in terms of
the trade-off in the sense, like if you have these two ways of analyzing it, I assume you win something or something is better than the other depending on what you choose to, what method do you choose to analyze?
No, these are two. I mean, it's not that. Okay, these are two different definitions. Like, and one is definitely stronger than the other.
I
right?
see.
Because full-fledged simulation extractability says, like, look, the only thing you can do is copy-paste the pair statement and proof. Weak simulation extractability says, if you have seen proof for X1, X2, X3, you cannot come up with a proof for a different X star.
Sure. Okay.
But you may come up with a different proof for X1, for example. Right? So we're going to see that, I mean, some schemes have this property. And sometimes this can be efficient because in some context, having the possibility of taking a proof for some statement and just re-randomize it and get a fresh proof for the same statement could be useful when, for example, if you have to, let's say, authenticate yourself for anonymity reasons, like you don't want to expose the same proof several times.
Definitely. Is there any other use case aside from re-randomization of proofs where this can be useful?
You mean weak simulation extractability?
Yeah, exactly.
I think it's up to the application. So, like in some application, yeah, I don't have something in mind, but like, yeah, it really depends on the application. Like if
Sure.
Sometimes, I mean, let's say re-randomizability is a good use case where, where anonymity is a good use case where randomizability is useful.
Makes sense. Makes sense.
Let's say that maybe strong simulation extractability could be easier to use in some applications if you can exclude that something has been, let's say, seen, and you want to discard proofs that are copy pasted, let's say.
Okay.
So if you have a mechanism to keep track of what has been produced, for example.
Thank you.
Okay, so, why do we care about simulation extractability? I mean, first, because this notion actually implies that proofs are non-malleable. I mean, essentially, it's really intrinsic in the fact that it implies the fact that you cannot, given a proof for X, you cannot come up with a proof for X prime without knowing a witness. And that's what, for example, like, Tsai that introduced this notion of simulation soundness, wrote in this sentence, like, essentially, this implies that whatever one can prove after seeing an easy proof, one could also have proved that without seeing it, except for just duplicate the proof. So there are two maybe important reasons for non-malleable proofs. One is that that some real protocols may require this, and actually I'm going to give you an example in the next slide. And another reason is more, if you're a cryptographer and you care about provable security, one realizes that the need of this in real protocol comes from a provable security reason, that often when you have to prove security of a scheme, you will be in the situation where your adversary does not just receive, let's say, the CRS and produces a proof, but is seeing simulated proofs. And that shows the need of having a stronger notion that, and not just knowledge soundness. Okay, so I'll give you an example of why would we care non-malleability with something that maybe is some example that is close to maybe people in this audience, which is the need of non-malleability in some blockchain protocols, in particular in anonymous cryptocurrencies. So what I'm describing in the slide is a very part of a toy example of the zero coin cryptocurrency, which it works like this. So there is essentially a coin. What we call a coin is actually a commitment to a serial number with some randomness R. Okay, so the coin is the commitment. And if you own a coin, it means that you know this serial number and this secret R. Now, the blockchain keeps track of two sets: the set of minted coins, so coins that have been produced and accepted to be valid, and we'll see how you accept to be valid. And then some set of spent serial numbers. So serial numbers that have been already used and you cannot reuse anymore, otherwise you would have a double spending attack. Now, how do you spend a coin in such a protocol? So we have our friend here, our hedgehog, that has a coin A. And in order to spend this coin anonymously, what it does is to create a transaction that contains the set minted coins and the set spent serial numbers, or if you want, maybe hashes of these sets. The serial number of his coin as NA, and a new coin B. Okay, so the idea is that now the user is spending a coin A and is transferring the value to coin B. And notice that the serial number of A now becomes public. So in order to make this transaction, he attaches a proof pi that is a proof for the fact that he knows a coin, right? So the coin is secret. So he knows a coin. He knows the randomness of this coin, of this commitment, such that essentially this relation is satisfied, which says the coin is in the set of minted coins. So I don't show you which coin I'm spending, but it's there. And the coin A is a valid commitment to some randomness that I know, right? And to the serial number that I'm exposing. Now, what happens now is that what the validators will check, they will check that the proof is valid, so that these conditions hold. So this coin is in the set of minted coins, and it's, you know, it's a coin with this serial number. And then they will additionally check that the serial number has not been already spent. Okay, so if this is, so if this happens, what they do is to progress. So the state of the blockchain changes by adding coin B to the set of minted coins. And then the serial number A now is a burned serial number, and it gets into this set. Okay, so let's now see how you could use malleable proofs to essentially break security of this cryptocurrency. So let's say now we are in this state where this guy has produced this transaction. So he has spent the coin A. So coin A should not be valid anymore. And then there is this adversary that just observed this transaction to happen. So she knows the transaction statement, and she knows the proof. Now, what she can do with a malleability attack, you know, if the scheme is malleable, she could, for example, now create a new statement that contains the, you know, the updated sets of coins, so minted coins prime and spent serial number primes. She can come up with a new serial number SN prime A and some other coin C, and a proof that essentially attests that this is a valid transaction. Now, if the proof is valid and this serial number is not in the set of spent transaction, then the validator will have no other choice than adding coin C to the set of minted coins. So which means that now you have created a coin out of thin air. So, you know, if you want it, like sort of double spending coin A, but in some sense it's about creating by creating a fake proof. Now, I'm not saying that, you know, for now, I'm just assuming a general malleability, or if you want some very strong malleability attack on this proof system. But the idea is that if you have seen a proof, and if you can come up with another proof without knowing the witness on a different statement, then this is a problem. Now, in the zero coin or zero cash that use this approach, this is not possible because there are additional checks in the relation that you prove. But, you know, if the proof system would be non-malleable, that, you know, you could get for free this property. All right, so this is to motivate why do we care about non-malleable proofs. Now I'll move to the second part of the talk, which is how can we construct simulation extractable proof system, in particular simulation extractable SNARKs. Okay, so I have to, I want to mention like that, you know, in these first works, when I introduced the notion of simulation soundness and also extractability was introduced by Groth in 2006, they gave specific constructions of schemes satisfying these notions. And I have to say that there is a large body of research on this, and it's not my goal here to talk to you about, in general, about simulation soundness and state of the art of simulation soundness or simulation extractability for NISIC. The focus that I want to put here is on just simulation extractability for zkSNARKs, that are this class of NISIC where proofs are succinct, right? And these are very, you know, popular nowadays for their appealing properties, for example, for decentralized protocols. So, okay, what can we say about simulation extractability of zero-knowledge SNARKs? You know, one observation is that most zkSNARKs that are out there are only proved knowledge sound, okay? And this is, one could say, okay, why this is the case? I mean, first of all, because normally in a research path, I would say, like, that's the first thing you want to obtain, right? So the first non-trivial property is how to obtain that something is sound. But there is more to it. So another observation is that actually many of these, some of these existing constructions are malleable. For example, Pinocchio and Growth 16, that were these first popular zkSNARKs, have re-randomizable proofs. But then also another reason is that proving simulation extractability is extremely challenging. Because it's a complex property, and so often it does require like additional work that, you know, essentially it's worth probably like additional research. So it's a sort of a second step in the research on zkSNARKs. Okay, so let me now go to the question of how do we construct simulation extractable zkSNARKs. So there you know, on the good side, I have to mention that there are generic ways to go from just a NIZK to a simulation sound NIZK. This has been proposed since the early days of when this notion was proposed by De Santis, De Crescenzo, Ostrowski, Persiano, and Tsai in 2001, where they gave a compiler. The drawback of this compiler and some more recent and efficient variants is that still it blows up the proof size. So this is not a problem for NIZK, but it's a problem for SNARKs, because like you go from a scheme where proofs are, let's say, logarithmic in the length of the witness to now something that is linear, that is usually what you don't want. So now let me analyze what happens to the first generation of zkSNARKs that, you know, I call first generation like the schemes that have trusted and circuit-dependent setup, like, for example, Pinocchio Growth 16. So these schemes have re-randomizable proofs, so strictly speaking are not simulation extractable. And that actually motivated Groth and Mahler in 2017 to propose the first efficient simulation extractable zkSNARK with short proofs, which essentially was, I mean, it's a scheme that is a bit less efficient than Groth 16. Well, maybe no, it's less efficient, right? Not only a bit, because it's also a scheme for a language that is not just quadratic arithmetic problems. And now another thing I want to mention is that actually, like, in a, I mean, I would say, yeah, in a more recent result, Bagheri, Kolvais, Sim, and Volkov have proved that Groth 16 has re-randomizable proofs, but actually that's the best malleability that you can do. So in the sense that it is weakly simulation extractable. Okay, so this requires, I mean, it's weakly simulation extractable in the AGM, in the algebraic group model, but it does require some additional properties that, I mean, I'm not going to discuss, but I refer you to the paper if you're interested about it. Okay, so what about, you know, what we can call the second generation zkSNARKs? I mean, I have to say also in the first generation, there are other schemes that are simulation extractable, but this is, let's say, what are maybe the very first ones. Okay, so let's now consider like schemes with these universal and transparent or maybe updatable setup algorithms. So in this case, there are some recent results that show that, for example, bullet proofs is simulation extractable in the AGM. A more recent result shows that Spartan and bullet proofs are simulation extractable, but now under the very same assumptions under which they are knowledge extractable, or knowledge sound. And finally, another work by Ganesh, Koshak, Kolvais, Nitulescu, and Zajac from 2022 shows that Sonic, Plonk, and Marlin are simulation extractable. And they do this by showing a framework based on two notions called unique response and raptorless zero knowledge. You know, the drawback, I mean, this is what I want to say in general about the state of the art, is that, as you can see, all these results are quite ad hoc. So even this recent one that gives some framework has to introduce new properties that you have to show for each scheme, such as this raptorless zero knowledge or unique response, that essentially require to reanalyze the security of each scheme. So So this state of the art is what motivated our work. That is this paper that is going to appear at TCC 2023 called From Polynomial IOP and Commitments to Non-Malleable zkSNARKs. So essentially the question we asked in this paper is, let's consider all these universal zkSNARKs that are obtained using this modular framework that consists into taking the polynomial IOPs, polynomial commitments, and putting them together using the Fiore-Shamir transformation. And the question we ask is, under what conditions are they simulation extractable? Okay. You know, very briefly, a spoiler of our results, of our contributions, is that we actually define a notion of a weaker notion of simulation extractability for polynomial commitments that we call policy-based simulation extractability. We show that KZG satisfies this notion for some policy phi. We give a notion of compilation-safe polynomial IOP, so essentially some conditions on the polynomial IOP that have to hold. And then we show that if you compile, you know, if you use zkSNARKs using these two objects, you obtain simulation extractable zkSNARKs. And this allows us essentially to imply the simulation extractability of Marlin, Plonk, Lunar, and Basilisk. But although, I mean, I will explain not exactly the schemes, the more optimized schemes. Okay, so that's actually an interesting open problem. Okay, so okay, maybe like do a quick breath to, I mean, just to breathe, and this is the outline how I'm going to present this result. Okay, so I'll first give a quick introduction to what are polynomial IOPs, polynomial commitments, and what is this modular compiler that allows to build zkSNARKs using Fiore-Shamir. Then I'll describe that actually this approach is vulnerable to some malleability attacks. And then I will discuss how we can patch them, and I will also mention that you know, we'll study the malleability of KZG, and finally I will give what is our recipe to obtain simulation extractable zkSNARKs. All right, so okay, so polynomial interactive oracle proofs are an information theoretic proof system that is defined, actually, you know, precisely I should have said polynomial holographic interactive oracle proofs. So it's a proof system for index relations. So these are essentially NP relations that in which the relation consists of three elements: an index, a statement, and a witness. And you can think that the index is like an index of a relation. So it's a way to model so-called universal relations. A classical example is that R could be the you know, the family of relations that contains all circuits of a certain size and all, you know, statements for which the circuit is satisfied, right? So, and the index models which circuit you are going to use. The statement is the input of the circuit, and the W is the private input of the circuit, for example. Okay, so in a polynomial IOP, what the first algorithm that you have is the so-called indexer. So the indexer, what it does is to take the description of the relation that you want to prove. Think that you take the description of the circuit. It outputs a set of polynomials that, a set of polynomials that describe the circuit. Okay. And that's something that, okay, it's maybe I should have not put it like this in the slide. It's not generated by the prover. So this is something that is, for example, generated by the verifier. Okay, so but it can be done in an offline phase. Then the protocol between prover and verifier consists of several rounds. So it's an interactive protocol. the verifier is just a so-called public coin verifier. So at every round, the verifier simply samples a random field element, let's say row 1, and sends it to the prover, and the prover answers with a polynomial. Now, this polynomial is not really given to the verifier, but is an oracle, right? So it's sort of a polynomial that is there in the sky, and that later the verifier will be able to query in some way. But the prover is essentially sending it. Okay, so again, remember this is a sort of an ideal proof system where we are assuming that, yeah, the prover can, later as we can see, can be arbitrary, but then, like, you know, these oracles are there in the sky. So the verifier will trust that things with the oracle will be done correctly. Okay, so this goes on for several rounds. So every round, the prover sends a polynomial, then later the verifier responds with a challenge, and so on. Now, when these rounds end, what the verifier outputs is what we call a polynomial check. So it will output a multivariate polynomial G and a set of other polynomials V1 and Vn. And, you know, you can output K of them, I mean, or several of them. And the idea is that the verifier accepts if these equations, so if for every K, this polynomial GK is identically to 0, when GK is computed on X, and the evaluation of each of the oracle polynomials on the ith VI polynomial on X. Okay, so this is a very general way to, for example, model different type of queries that you can do. For example, if you want to model that the verifier wants to test evaluation of P1 on I don't know, point Z, then it would set the polynomial V1 to be the constant polynomial with constant term Z, and that, you know, and then maybe you can put in the coefficient of G, the fact that you tested something is equal to 1. Okay, so this is in fact, this notion, this way to model verifiers is the notion of polynomial holographic proofs that we propose in Lunar, that generalizes the notion of algebraic holographic proofs and ILDP, and LDP from respectively Marlin and Blanc. Okay, so in terms of security in a polynomial LP, we want knowledge soundness, and I mean, I will describe it only informally. It says that there exists an extractor such that for any prover that convinces the verifier, the extractor, by interacting with the prover, can extract a witness. And then honest verifier zero knowledge. That means that there is a simulator that can simulate the view of an honest interaction between prover and verifier without knowing the witness, of course. Okay, so remark again. The remark here is that this is an ideal protocol in the sense that when the verifier outputs this decision, this way to decide whether to accept or not, which is these G polynomials. This test is not performed by the verifier. It's performed by, let's say, a trusted party that has access to the oracle polynomials and can do this. Okay, so and the idea is that then we will replace this ideal part with a polynomial commitment. So very briefly, a polynomial commitment is it's a sort of a proof system that allows you to generate first a CRS, with a setup algorithm. And then you can commit to a polynomial P, and produce a commitment C. And then what you can do is to prove evaluations of this polynomial on a given point X. Okay, so the proof algorithm produces a proof, for example, about the fact that Y is P of X, where little x is an evaluation point. And then there is a verification algorithm that, given a commitment and two values X and Y, and the proof accepts or rejects. So one important observation that we are going to use in our work is that this prover and verifier algorithm essentially are a commit and prove SNARK for the relation that says C is a commitment to P, and P of X is Y, right? So because requiring that the proof is succinct essentially is equivalent to saying this, that the polynomial commitment, we can see it in this way. All right, so how now can we use polynomial IOP and polynomial commitments in order to build a SNARK? So the idea of this compiler, that this is not our work, so this has been used essentially in many previous works, is that the way the CRS of the SNARK that we produce is actually the CRS of the polynomial commitment. Now, the derivation algorithm. So, what is the derivation algorithm in zkSNARK? So, it's this algorithm that can produce a verification key that is just specific for a circuit, let's say. Okay, so this derivation takes the CRS and the index. So think of it that it takes a description of the circuit and produces a verification key for that circuit. And this is a deterministic algorithm. And the idea is that it runs internally the indexer of the polynomial IOP, gets the polynomial P zeros, and it commits to them. And that's your verification key. Now, how do we generate proofs? The prover of the SNARK on input the index, the statement, and the witness will run internally the polynomial IOP prover, with the difference that instead of calling the verifier interactively, it will use the random oracle to replace the interactive part of the verifier. So, for example, it means that row 1, instead of being given by the verifier, is actually produced by the random oracle on the transcript that starts with the verification key for the relation and the statement. Then the prover uses this challenge to produce the first polynomial P1 using the polynomial IOP prover, commits to it, and then again gives it to the random oracle, and so on and so forth, and this goes for R rounds. So there is no interaction. So the prover essentially interacts with just the random oracle, which in fact, in practice, then it will be an hash function. Okay, so then the last step consists into intuitively into proving that the polynomial IOP verifier would accept if with these polynomials P1, PR. So when we use polynomial commitment to do this, we do this in the following way. So recall that the goal is to prove that for all k, this polynomial is 0. And this is a polynomial equation. So there is an indeterminate x. So in order to prove that this holds, we will sample another random point, a row R plus 1. Again, it will be given by the random oracle. And then we prove that evaluation of this polynomial on row R plus 1 is 0. And however, how do we do this? By essentially computing each input, so each VIK of row plus 1, which is the input of the polynomial PI in this verification test. That's the input, and then we compute the output, and then you add an evaluation proof that YIK is equal to PI of XKI, for every I and K, or for every I and K that are involved in the test, GK. Okay, so this is if you want to link it to something that you may know, like if you know Plonk, for example, in that case, all these VI polynomials are essentially the identity function polynomials. For example, it's just X, and in one case, actually, you do it on this omega times X, so where omega is this root of unity. So maybe this allows you to, for those familiar with Plonk, to link to what you know. Okay, so so that means that the proof of the SNARK consists of all the commitments that you produced, right? So the commitments to the polynomial IOP polynomials, and then the outputs of the evaluations of all the polynomials that are involved in this test. and the respective evaluation proof of the polynomial commitment. What the verifier does, the verifier will be able to just, by reconstructing the transcript of the random oracle, will be able to produce the same test polynomials, right? And then it will check that the evaluation of rho r+1 is 0, given these promises given by the prover, the yki values. But in order to since the verifier does not trust the prover, it will have also to check that the evaluation proofs are correct, right? That for each, that if Ci is a commitment to polynomial Pi, when you evaluate it on Vik of rho +1, which is the input of the polynomial, then you get yki, right? So that's essentially this, you want to prove this statement here. All right, so this is the compiler, okay? And several works have proved that essentially this compiler gives you knowledge sound SNARKs, right? If the polynomial IOP is knowledge sound, and if the polynomial commitment is essentially like knowledge sound as well. Okay, so the question we ask here is that whether these zkSNARKs are simulation extractable. Okay, so, and I'm going to show that actually, in a universal sense, they are not. So there are actually 3 potential attacks that you can mount. Okay, so okay, so the first attack, this is more like a feasibility attack. So, okay, so maybe it's not a natural one, but it shows that something may go wrong. Consider the following relation. So it's a very simple relation that, for example, tests for hash preimages of 2 values. So in the public statement, we have 2 values, x1 and x2, and you test that, w1 and w2 are hash preimages of x1 and x2 respectively. And assume now that you have a polynomial IOP to just prove, one execution of the hash, right? So PyOP-H is a polynomial IOP protocol that can prove that x1 is hash of w1, and or x2 is, any x is hash of some w. Okay, so, and for some reason, this is maybe the artificial part, assume that in order to design a protocol for proving the conjunction of these 2 hash computations, you compose this polynomial IOP with itself in a sequential manner. Okay, so it means that you first run the polynomial IOP on input x1, w1, and then you run the polynomial IOP on input x2, w2. So, this is what is in the picture. And we're assuming any polynomial IOP, and it's a good one, right? So it's not that we're assuming an insecure polynomial IOP. Now, when you plug this in the compiler, your proof is something like this. So you have, here I'm just using what we have in the previous slide. So the proof consists of all the polynomials C1, CR for the first execution, along with whatever are the evaluations that you need to test this polynomial IOP and the evaluation proofs of the polynomial commitment. And then you will have another set of commitments and evaluations and evaluation proofs for the second part of the protocol, that is the second execution of the polynomial IOP, but on the other statement. Okay, are you with me on this?
Yep. Yeah.
Okay, so now one crucial observation is that if you compile this PyOP obtained by the sequential composition in a standard way, what one would observe is that all the evaluation of the polynomials of the first execution will depend on a random challenge that is chosen even with the random oracle, only depends on the first part of the protocol, right? So because if you compile it in a standard way, like you would stop here, and then the test, or you would run the verifier on X1, and you test at this point. So, but this verifier doesn't know this other execution, so we'll just give you like tests that depend only on the first, the first part of the protocol. So with this observation, we can mount the following weak malleability attack. Okay, so consider an adversary that chooses like an X1 at random, right? So this means that it's a string for which, plausibly she doesn't know the preimage, and then chooses X2 so that she knows the preimage W2. Then she asks a simulated proof on X1 and X2, and she gets it. And this proof is, we can parse it as two portions, like pi1, which is the, it's exactly as in my slide. So it's the proof for the first part of the polynomial IOP protocol, and then pi2. Now, the observation is that, let's say that she can compute another pi2 star by running the polynomial IOP prover for the second statement, but with fresh randomness. And I'm speaking about the randomness of the prover, right? The randomness that you would use to make it zero knowledge. So that will cause the following thing. So at some point, if this polynomial IOP is zero knowledge, some of the polynomials in the second execution of the protocol, like here in the red part, will differ from the polynomials in the other execution, even if you reuse the same witness W2, right? Because it's simply you are using, for example, you randomize the polynomials using different randomness. So the moment the polynomials change, like also the commitments will change. So this transcript will diverge. So this proof it's why this proof pi2 star is different from pi2. And but the concatenation of pi1 and pi2 star will be accepted because essentially the verification of the two parts is independent. And in particular, the first part, the random oracle, the polynomials of the first part of the proof are going to be evaluated on points that do not depend on the second part of the proof. So the random challenges essentially that here are the same as in this proof. So if this pi1 passes, this one will pass here as well. So, and that shows how you can create a new proof for the same statement for which you have seen a proof. Okay, so that's one. Yeah, I see a question. Go ahead.
Yeah, sorry. Wouldn't this be actually an attack because we didn't perform Fiat-Shamir correctly and we didn't put all of the witness in as input of Fiat-Shamir? But so it's not necessarily because we have two PIOP. We could have the same. Error if we don't commit to all of the witness.
Right. Okay. Let me clarify this. So in Fiat-Shamir, you don't hash the witness, right? Because the verifier will not have the witness. You hash the statement.
Yeah, sorry.
And that's why, like, if you notice in my example attack, the statement is going to be the same. So when you run this X, so in the first and the second execution, you do it on the same X.
Yeah. Sorry, right? My bad.
So, but it's a good question. I mean, it's in some sense, this shows that it's only a weak malleability attack and it's not trivial to extend it to, let's say, to change statement. Okay. Now, one good question that this is, let's say, a warm-up, because I'm showing that an attack for a polynomial IOP that maybe is not so natural, right? Because it's, okay, I mean, actually, this would be very unnatural to do sequential composition. If you are just proving two statements that are disjoint, you would actually probably parallelize it. But now I'm going to show what that actually it's similar attack would apply to polynomial IOPs that are very natural because actually they are the polynomial IOP that are underlying Marlin and Lunar. So in this attack, I'm considering a broad class of polynomial IOP that I call to a delegation round. So what's a delegation round? So we say that the polynomial IOP as a delegation round is if at some point of the polynomial IOP protocol, you are sending a commitment, or in general, you are sending a polynomial that only depends on the index polynomials and the previous random challenges. And that's actually something that happens in some polynomial IOP, because the last round typically is about essentially having a polynomial that is a compression of the description of the circuit, or for example, of R1CS matrices. And the verifier would actually know this polynomial, but it doesn't want to evaluate it because it's too large for the verifier. So it's delegating the evaluation of this polynomial to the prover. Okay, so important thing here, crucial, is that the prover is sending a commitment to a polynomial that is public, and the polynomial is going to be evaluated. Well, actually, no, and that's it. So the important thing is that it's public. Okay. Now, but another observation that actually is important for the attack is that all the polynomials that were sent before this delegation round will be queried on points that depend only on challenges before the delegation round. Okay, so that means that essentially these polynomials V1 of K are constant polynomials in their input. And again, this is a property that polynomial IOP, such as those in Marlin and Lunar, satisfy. Okay, so it's not, this is to claim that it's not something unnatural now. But again, for such the compilation of such polynomial IOP, we can break the proof in two parts. So there is the part, for the first R-1 rounds, and then there is the part about the last round. Now the attack would go as follows. So the prover would ask a proof for X, for a statement X. Again, the attacker doesn't know the witness for X, but she gets this proof by 1, by 2. And then she computes a different by 2 part by just, for example, computing a fresh commitment to PR of X. Okay, so here I'm assuming that we are compiling this with an ID polynomial commitment. Okay, so you can commit again to the polynomial. The polynomial is the same in both executions, but when you generate a commitment with fresh randomness, the commitment is going to differ. Now, the moment you send a different commitment, the randomness that comes after it, so the random oracle computed on this commitment, will give you a randomness row R+1 star, which is different from the one of the other execution. So, and then the important thing is that since the polynomial is public, the adversary can compute honestly evaluation proofs with respect to this fresh commitment, because she knows the polynomial, right? There is nothing hidden in there. And that's essentially the new proof. So you have X star is actually X. So again, this is a weak malleability attack because we are not creating a new statement, but it is a statement that we have already seen, but we came up with a new proof for the same statement. Okay, so is this clear? And I will recap about maybe what we can learn about these attacks.
I think everything has been clear so far, yeah.
Yeah. Okay, so, and then I want to show a third attack that is an attack that would work regardless of the polynomial IOP protocol. And it would be based on the fact that, on the possibility that the polynomial commitment is malleable. I'm not saying that polynomial commitments have to have this malleability, but it's to show that if they are malleable, or then this is a problem. So first of all, what does it mean, polynomial commitment malleability? For this slide, we're assuming that given an evaluation proof pi that is accepted for commitment C, point X, and output Y, then you can compute another commitment C star and another proof pi star that are valid for C star, X star, and Y star, where X star is different from X. And Y star, we don't care. Maybe the same, maybe not. Okay, so if you have any polynomial IOP and you compile it with such polynomial commitment, the proof would be the usual proof. It consists of all the R commitments and the corresponding evaluation proofs. Now, what the adversary can do is to first ask a proof for X, right? So for some statement X for which she doesn't know the witness. She gets the proof, and then she executes the protocol again for another statement X star. So she tries to essentially execute this protocol following the honest execution, but she does the following. So whenever she has to send a commitment, she actually sends a commitment C star I that is obtained by using this malleability attack. So, I'm not saying how to do it. It's just that, it's possible to get, given CI, it's possible to get a commitment C star I. And that's what she plugs in the protocol. She gets random challenges, right? So the random challenges are going to be different from the ones of the of the proof that she has received because commitments are changing, and also because actually the statement is different. And then she can use this malleability attack in order to come up with a different proof for this new statement. And this of course is possible if it is possible to break malleability of the polynomial commitment, because she has seen these blue proofs for this other statement X. But there is a simpler way, if you want, to see that this is malleable, in terms actually it's weakly malleable. If the polynomial commitment admits re-randomizable proofs, then it's actually trivial. You just get a proof for X and you re-randomize just evaluation proofs, and this gives you a different proof for the same statement. Okay. Okay, let me recap what I've shown. So in case you got lost. So I showed 3 attacks against the simulation extractability of zkSNARKs obtained using this paradigm of compiling polynomial IOP with polynomial commitments and Fiat-Shamir. Right. So what lessons can we learn about these attacks? Because there are important observations that we can make. So so if you remember, the first attack is this sequential polynomial IOP composition. And there this is also so a common issue in attacks 1 and 2 is that there could be polynomial IOPs in which some polynomials are going to be evaluated on points that don't depend on the last round, or they only depend on certain rounds, let's say, right? So and this is a source of issue. So it was a source of issue in the sequential composition, but one could say, okay, look, maybe sequential composition is artificial, but actually it can be an issue in protocols where you have this delegation round, where essentially it's a protocol where you could stop at a certain round if you don't care about efficiency, and then you move on just to obtain efficiency. But this class of protocols would suffer of the fact that the point where you would have stopped, now you would query the polynomials on points that don't depend on what you send next. Now, I want to mention this delegation round is not present in Plonk. So actually, Plonk would not suffer this vulnerability. And is present in Marlin or Lunar, but it is actually fixable in the sense that you could add an artificial evaluation of these polynomials on, or actually all polynomials on a fresh randomness, and this would actually remove this vulnerability. Yeah, go ahead. I see a question.
If I recall correctly, the way on how to fix these protocols such that these issues do not happen also comes together with your work on this paper, right?
Yeah, right. We're going to see, yes.
Okay.
In some sense, we define a general condition that a polynomial IOP might have to not fall in these under these attacks.
And is it then explicitly proven for such schemes, or you just leave it in the general case and anyone can then analyze it?
It's a very, no, it's well, it's something that it's most improved. It's something to check, right? So
Yeah, sure.
it's because it's a very simple problem. You just need to check that there is a query to all polynomials on a random point that is sent at the very end.
Okay, so it's some sort of recipe that for these past things, I mean, you can do the analysis there, or anyone can do it for the future schemes. It's just a recipe that you can include, and you just get simulation extractability or knowledge soundness directly.
Right.
Sure.
But I will also mention that actually we have another ongoing, we have ongoing work to avoid applying this patch.
Okay.
So and maybe one thing that right. So I didn't stress too much is that for this second attack with the delegation round to work, the commitment must be an hiding commitment. So, for example, like it's curious that maybe accidentally, like for example in Marlin, where they said, okay, look, since what you commit is to a public polynomial, you don't have to make it commitment. So the general compiler recipe says that you just use the commitment scheme as it is, but then in the optimization paragraphs they say, oh, actually you don't need to use an hiding commitment for this round, so you use a deterministic commitment. And it turns out that if you use a deterministic commitment there, and let's say proofs are unique, you would not suffer this issue.
Makes sense. Thank you.
Okay, so the third attack, which is the one that would rely on this potential malleability of the polynomial commitment, is the most devastating, because as we have seen, you could even make a proof for different statements. Now, an observation that for now we'll keep it high level is that this could be fixable if we require the polynomial commitment to be simulation extractable. Okay, so this suggests that maybe the tentative goal of that we could achieve could be something, a compilation recipe that is the following one, which could say, okay, take a polynomial IOP, but not any polynomial IOP, like one where all polynomials get evaluated on some challenge that is given at the last round. Then use a polynomial commitment is simulation extractable, and then use Fiore-Shamir as we described, and then what you get is a simulation extractable zkSNARK. Now, this recipe may work. Honestly, we didn't prove it in our work. But the problem is that, and this was also our interest, is that it would not capture existing constructions. Why? Because the many constructions that we know rely on this KZG polynomial commitment that is quite malleable. And I'm going to show some malleability attacks in the next slides. So that would be a problem, because then, okay, this goal would not stand because this assumption is not satisfied by several instantiations. So, okay, so I see that I'm already on over 1 hour.
For us, it's no worries. Like you can take as much as you want, since it
but I try to maybe to keep it in 15 more minutes or something like that.
Sure.
Because I guess also people may get tired, and it's hard to follow. All right. So next steps, I'm going to show you first what malleability or non-malleability you have in KZG. And then our trick will be to see that actually the attacks that we can mount, the malleability attacks against KZG that we can mount, do not help to break zkSNARKs, and we can show this provably. And essentially, we will show a sufficient condition that KZG meets, and that allows us to obtain simulation extractable SNARKs. All right, so so is everyone here familiar with KZG? Because maybe this is something that I could, where I can go very fast.
I think we can just assume it for the sake of time. If you want, we can just assume it. But okay. Happy to listen to the explanation, to be honest. But if you want to summarize and go faster, you can definitely go over it.
Okay, I'll go very fast. So here, maybe just to set, maybe it's more important to set up the notation that I'm using so that you will follow the next slides. Okay, so we are using bilinear groups of prime order P, and I'm using this additive notation and bracket notation for group elements that essentially for some fixed generator. So if you have a group, let's say G1, and you have its generator little G1, to denote G1 to the power of alpha, we're using this bracket notation where we put alpha inside the bracket and the subscript in, refers to which group we are in. And then I'm modeling everything as additive groups and additive operations. Okay, so the CRS of KZG is these powers of a secret point S given in the exponent. So like in group 1, and then we keep just the generator G2 and G2 to the S in group 2 for some random S. How do we compute a commitment to a polynomial P? We just compute in the exponent P of S. So this can be done because if you have the coefficients of P, you can just do linear operations in the elements of the CRS. And then in order to prove evaluation in a point little x, what you do is to compute in the exponent this polynomial Q, which is the result of dividing P minus the result P of x divided by the polynomial essentially. Okay, so I use bad notation, but it's like capital X minus little x, right? And the proof is the evaluation in S of this polynomial Q. And how do we verify? Essentially, the verification consists in using the pairing to check that pi is well formed. And the interesting property of KZG is that this proof is unique. So there is only one pi that satisfies this equation. All right. So one thing that maybe not everyone may be familiar with is how do you simulate proofs, and what does it mean actually to simulate proofs? So let's say that you want to now simulate a proof for commitment C, input X, and output Y. The way you would create a simulated proof is by taking C, you subtract the encoding of Y in the exponent, and then you exponentiate to the inverse of S minus X. So this is a way to create this unique proof for this statement. And clearly this requires the knowledge of the trapdoor S. Okay, so this is the simulator, the simulator for the proof algorithm. Okay, so I was saying that KZG is malleable, and I'm going to show you, some simple attacks. So this is not new because it's based on the fact that KZG is actually, has an homomorphic property that is actually a useful property. So assume that you have a proof pi for CX, commitment C, input X, and output Y, and this means that it satisfies this equation up here. Then it's very easy to create a proof, which is actually the same proof, that the same proof holds for a different commitment, C plus some delta, and another result, which is Y plus delta. This is trivial, and if you want, the intuition is based on the fact that if you have a proof for evaluation of a polynomial P on Y, if you shift the constant term by delta, the output will be shifted accordingly by Y. So that's, and then another way to see is that the same, essentially plus delta here and minus delta will cancel, and that's why the same proof holds. What is perhaps more interesting is that you can also create proofs for different points if you can change the commitment. So, okay, let's say that you have seen a proof for commitment C, input X, and output Y, and now you are given an arbitrary point X star, and you create C star as C minus the proof pi multiplied by X star minus X. Okay. And then X star is the input, and Y, the same Y that was the output for the other proof, we reuse it. Okay, so I'm going to show, or you can see, actually check what is in the slide, that pi star, so the same pi star equals to pi, is a valid proof for this fresh statement. And notice that, if you have seen a proof for which you don't know the witness, which means that for which you don't know the polynomial, one is able to generate a proof for something for which you don't know the full polynomial inside, yet you can generate a valid proof. I mean, and you follow this equation that tells you why that this is still a good proof. And yeah, I mean, okay, I can read it, but it's really what you have to do is to take the verification equation for pi star, observe that S minus X star can be rewritten as S minus X plus X minus X star, right? And then you use the bilinear property to split this S minus X and plus X minus X star in two pairings. And then you use the fact that this is equal to C minus Y paired with 1, given the fact that pi is a valid proof for C and Y and X. And then here we use the fact that we are redefining the commitment C star as C minus this, well, maybe there is a minus sign that is wrong here. No, actually it's correct, right? So the commitment we redefine it as C minus this value times the proof, X star minus X times the proof. Okay, so okay, the good news, however, is that in spite of these malleability attacks, these specific attacks are not enough to break the simulation extractability of the zkSNARKs obtained by using this polynomial commitment in the compilation strategy. And so why is this the case? So for simplicity, assume that you have a polynomial LP where the polynomials are evaluated on directly the output of the random oracle, okay, as it is actually the most common case. Then what happens is that these attacks require to change the commitment. So the moment you change the commitment, you get a different random challenge. So that means that the first attack does not apply, right? Because the first attack is about creating a proof for a different commitment, but on the same point X. So now the input is changed because of Fiore-Shamir. But another thing that gives us Fiore-Shamir is that the moment you place your commitment, you don't know what the random challenge will be, right? And that also defeats attack 2, because in C star, so even if this work for an arbitrary point X star, you have to fix this point the moment you fix your commitment in the attack. Okay, so this defeats both attacks. In some sense, the interesting observation that we will use is the fact that Fiore-Shamir is of help in the fact that we get evaluation points after the commitment. But there is another type of malleability that you can mount, a malleability attack that you can mount if you are in a full-fledged simulation extractability experiment where you can ask arbitrary statements to the simulation oracle. So assume that you have asked a proof for commitment C and input X and output Y1, and then later another proof for same commitment C, same input X, and another different output Y2. So the simulator will be able to generate these proofs. And if you have these proofs, you can actually create a proof. Yeah, maybe I'll go fast on this because this is more technical and people will be able to check it on the slides by themselves. But the main point is that you will be able to create a commitment that does not depend on any point that you're going to see in the future. But then the moment you know a point X star, you can create a proof pi star about evaluation of, that passes the evaluation on C star for some point Y. I mean, actually Y star has a certain form, but if you then apply the attack 1, you can even do it for an arbitrary Y star. So, okay, feel free to check it. I mean, this is actually, I think we have it even in our paper. But what is important is that this shows that if you are in a full-fledged simulation extractability experiment, and you can ask these queries, then you can create an attack that works for any X-star that is chosen after the commitment. Now, a note is that this attack is a bit unnatural, if you want, because it's kind of really asking the simulator to prove something obviously false, right? Because essentially you're asking, can you prove that if you have something in this commitment on X gives you Y1, and then later you ask, oh, now prove me that it gives you Y2 for the same polynomial and the same input. So, right, so everyone can test that this is false. So, and actually this is why, this attack is of no concern for the simulation extractability of zkSNARKs, under the condition that the polynomial IOP way the way you prove zero knowledge in the polynomial IOP would not create this kind of strange queries. So essentially, as long as the the view that you simulate is consistent, is what we call algebraically consistent. It means that you are giving some evaluation outputs that form a system that admits a solution for which there exists a polynomial that can give you those outputs. Then you are not going to run in this strange case. Go ahead, Carlos. I see that you have
is this something that is also enforced or requested in the paper from about simulation extractability in, if I remember correctly, 1992, or I don't remember the year exactly, but the first paper that you mentioned where simulation extractability is defined? Is this kind of property something that is also asked?
No, because this is something very specific that you are asking for of polynomial IOP. Or do you refer to the fact that you don't ask false statements?
Exactly. Yeah.
No. Actually, it's if you're interested in this, there is in general in simulation soundness or simulation extractability, you can ask whatever you want, even false statements, and this should not help you to prove new false statements. Then there is a relaxed notion called true simulation extractability or true simulation soundness, in which you can only ask true statements.
Okay.
Yeah.
Okay. Thank you.
Okay, so an interesting observation is that, it seems the case, we don't have a proof, but it could be an interesting, something interesting to check, is that essentially any polynomial IOP that you want to use in the compiler would have this this property that essentially the view that you generate does not raise these essentially inadmissible queries. I'll jump fast on this. Okay, so based on these attacks, so again, recall that maybe very fast, we have seen 3 attacks. One shows that if you can change the commitment, you can create proofs for other statements, but it will not work if the evaluation point is chosen randomly after the commitment. And then this attack says, okay, if you can ask these sort of dangerous queries, you can also bypass this check of, essentially it will work. You can do attacks even if the point is randomly chosen after the commitment. Now, this suggested us that actually we could prove some form of simulation extractability for KZG. And this weaker form is a form that respects the following game. So it's a simulation extractability game in which the adversary has access to the CRS of KZG, can ask simulations of simulated proofs for commitments and statement input and output, and then has to produce a proof and the extractor must produce, must produce a commitment, input, output, and proof. The extractor should produce a polynomial, and we check that the proof pass verification, and that whether the polynomial is either not the committed polynomial or the evaluation is incorrect. Now, we even consider this game in the presence of a random oracle that, in the simulation extractability game is essentially simulated. Now, and the restrictions that we use in order to bypass those attacks, or actually to not consider those attacks, it's not that we bypass them, are the following. So first of all, we give to the adversary a set of points, QX, that for now, think that it's an arbitrary set of points, and then a set of simulated commitments. For simplicity, you can think that these simulated commitments are just random group elements in KZG, chosen according to some distribution. And then the first restriction is that whenever the adversary asks the simulated proof for CI, XI, YI, the point XI must be in this set that has been chosen at the beginning. Okay, so essentially we are saying the adversary cannot ask adaptively evaluation queries on points of her choice. She can actually choose these points at the very beginning, but not adaptively later. The second check is it's a bit technical check, but it's about algebraic group model. So if the adversary is in the algebraic group model, and whenever he produces this commitment in the query, he must also produce a group representation. So a coefficient representation of this group element CI. So this representation can be, so this commitment can be written as Fi of S plus some linear combination of the simulated commitments. So what this is saying, essentially, is saying that she cannot ask simulated proofs on commitments that are in the linear span of the simulated proofs that she has seen in the previous rounds. So this sounds kind of an unnatural restriction, but we will see that it will be sufficient for our compilation. And the last requirement is that all these simulation queries, if you look at all the pairs XI, YI, essentially must define an admissible system of equations. So it means that, for example, you cannot ask X, Y, and X, Y prime for Y prime different from Y. Like, this is the simplest example. So you cannot ask things that are obviously false in a certain way. And the last check that we do, is that the point X star chosen by the adversary, essentially it's randomly chosen after C star, and this is formalized in terms of random oracle, in the sense that the adversary must have queried the random oracle on the commitment, and the output of the random oracle is used to compute X star using some polynomial H that can be arbitrary as long as it's of degree at least 1. Right? It cannot be a constant polynomial. So, for example, this if you think again about Plonk, this H can be either the identity function, so X star is rho, the random challenge, or it can be root of unity times rho. So now, what we want here is to that the adversary and the extractor win if they play in this game under these rules. So this some simulation extractability means it's not that you can ask whatever you want and you can give us just something new. No, it has to fulfill these requirements. Okay, so this essentially tells us what is now going to be the strategy. Is instead of requiring that the polynomial commitment is just simulation extractable, we will require that is more or less like some simulation extractable. Precisely, we introduce a notion that we call policy-based simulation extractability, which is a generalization of simulation extractability that can capture both full-fledged and simulation extractability and other variants, because it's a parametric notion that depends essentially on the policy that defines the checks, the winning condition of the game. And then we identify a specific policy that is sufficient for the compiler to work, so to obtain simulation extractable zkSNARKs, and this so it's sufficiently strong for the compiler and sufficiently weak for KZG to meet it. Yeah, okay. Maybe at this point I'll go fast, because I guess it's I'm taking really a lot of time. Okay, so very fast. Like the notion of policy-based simulation extractability is simulation extractability with these additional checks that consist into giving to the adversary not only the CRS but also some parameters that we fix at the beginning. And then in checking that in the winning condition, not only something is, the adversary produces a valid proof and the extractor fails, but also that whatever the adversary produces satisfies certain condition that generically is, expressed by a policy, a predicate phi1. Okay, so in this sense, this is a very generic notion that is parameterized by whatever you put in phi1. Okay, so essentially it says it's simulation acceptability with additional conditions. So, for example, full-fledged simulation acceptability says that this condition just checks that X star pi star is new, right? So that's an example. Yeah, okay, so maybe I'll yeah, I think I'll go fast on this because
whatever you prefer. No worries, Dario.
Yeah, I see that. Yeah, I think it's relevant to jump to conclusions at this point. So anyway, so the very briefly on this slide is like we define the compiler, which is essentially the same compiler, but then the main point is that to prove that if you have a polynomial AOP with some extra requirements, if you have a commit and prove SNARKs for polynomial evaluations that is simulation extractable according to a certain policy, and you combine them using Fiat-Shamir, we get zkSNARKs that are fully simulation extractable. Okay, here I'm defining what is the policy and what are the requirements. I'll maybe discuss the requirements of polynomial AOP in the last slide better. And we show that batch KZG, so this batch version of KZG is simulation acceptable according to some policy that implies the policy that we need in our compiler. So that tells us that we can instantiate the compiler with batch KZG. Okay, so this is maybe the most important conclusive part, if you care about results. So our results and our framework imply that we can show the simulation acceptability of the following SNARKs. So of Plonk and Basilisk, Basilisk is this scheme by Raffles and Zapico from Crypto 2021. It has a structure not too different from Plonk. Now, for these schemes, we can show simulation extractability if you compile them without the so-called linearization trick, which is this trick that is used to reduce proof size when you have to prove some equation of this form. Let's say you have committed polynomial A, B, and C. You want to prove that A of R times B of R plus C of R is 0, something like this. And the trick says, okay, instead of sending you each evaluation, I can only send you, for example, B of R, and then I prove that this P of X polynomial computed in this way evaluates to 0. So unfortunately, we cannot capture this because it's a more complex way to prove essentially these polynomial checks of the polynomial IOP that escapes our analysis so far. But the good news is that in terms of polynomial IOP, the polynomial IOP underlying this Plonk and Basilisk satisfy the requirements that we need. Okay. You can probably see the paper for more details about that, unless you have questions that you're interested in. And then about Marlin and Lunar that have similar structure, we cannot capture the full-fledged protocols because of this delegation round. So that means that the original polynomial IOP failed to satisfy this compiler safe property. Essentially, is the property that says you have this evaluation in the last round of all polynomials. But if you add this to the polynomial IOP, then we can again capture them. But again, without this linearization trick. Okay, so to conclude, what we covered is an introduction to simulation extractability. We have seen what are the challenges of proving simulation extractability for SNARKs obtained using this compilation strategy. Hopefully, I gave you some ideas also, what's the challenge related to the fact that KZG is malleable if you care about SNARKs based on KZG. And then I showed, what is the recipe that you can use to obtain simulation extractability. So, I mean, probably some things are already apparent. So our work has some limitations. In particular, we still miss to capture the fully optimized variants that people actually use. And this is because of two reasons. It's because of the linearization trick and because of the delegation rounds that these schemes may have. And we have some ongoing work to fix this part. But on the other end, like the good part is that we have a general framework to because our goal was not just to prove existing simulation extractability of existing constructions, but to give a recipe so that people can just come up with new IOP, and with a few checks, they will know that they will be compiled to something that is simulation extractable. And another limitation is that our compiler part, is based on policy-based simulation extractability, is tailored to pairing-based polynomial commitment, because some of the properties that it uses are specific for algebraic adversaries in bilinear groups. And with this, I thank you for the attention. And I mean, I apologize for taking long time, but I hope this is useful to be checked offline. Actually,
you don't need to apologize for anything. It was really nice and really, really insightful. I have some questions. I want to leave room to Rafael in case he wants to ask anything, or any other person that is still here. Otherwise, I will ask. So I will wait a couple of seconds. Sure. So may I assume that you targeted or you consider KCG as, I at least got the intuition that seems to be the less strong polynomial commitment scheme in terms of simulation extractability. Hence, you targeted it so that you have enough flexibility for upcoming work, such that it can be adapted directly to this recipe, right?
Mm-hmm. Right.
Okay, that makes sense.
Yeah, in some sense, it's like, one easy way would be, okay, assume that your polynomial commitment is already very strong in terms of non-malleability, and you get something quite easier. But then this would leave out a lot of existing constructions. And in some sense, our motivation, that is the fact that, there are constructions that are used. And the question is, are they already simulation extractable? Because if they already have this property, we don't have to worry to change them.
Yeah.
Right. And
following this line, is this upcoming work and generally the trajectory that you're following now to try to come up with a fully generic, and whether you think it's possible, I guess that's the question, to come up with a fully generic recipe for upcoming work, such that simulation extractability can just be a list of checks that my polynomial commitment plus my construction needs to pass? Or do you think this is unfeasible, and there will always be the need to do some ad hoc work in order to check these kind of properties?
I mean, right now, in in terms of polynomial IOP, the checks are very easy. So actually, I mean, I didn't spend time to describe them, but the properties we ask, I would say that they are very natural. In fact, they are met by several constructions, except this delegation round issue. But we do think that this is bypassable. I mean, by just changing something in the way we actually without any changes, just by changing and going for a different analysis.
Mm-hmm.
So perhaps the main limitation right now is like, maybe capturing a broader class of polynomial commitments. I think it is doable. What I find challenging, and maybe it's my personal experience with this type of work, is that often when you want to be very general, you have to consider a lot of corner cases, right? Like especially it's like when you have to analyze things after the fact, right? It's probably what happened with many. I know sometimes I like to say that what we have been doing is similar to what people have been doing with like TLS protocols years ago. Like what the very first versions were not designed with many a lot of provable security in mind, or with they were designed with some basic properties in mind. But then people developed a lot of theory, and it was very difficult to catch and model them formally. And here is something similar. Like people have designed protocol with knowledge soundness in mind, which makes perfect sense because it's the very first property that you want. Knowledge soundness is very tricky. So with this, what I mean is that sometimes we realize that without any further costs, if you might have had the polynomial IOP that was slightly different, and it would have matched our conditions in a more natural way.
I see.
But maybe the two options were equivalent, and one would go for something. What is actually also interesting is that nothing seems to break down, right? So in some sense, like maybe even unconsciously, like this design is the designs are resistant to malleability attacks.
That's fair. Although it's also true that maybe there's not enough research or I don't know how to say it. There's not enough manpower, to put it on some sense, to try to catch up these things, so that maybe nothing breaks so far, but because we haven't done some analysis, and I ignore that, of course, because I'm not deep into this topic, but I don't know how broad and extensive this line of research is.
Personally, I don't think they don't break because we have not analyzed it. Because I mean, our work, for example, gives evidence that they are simulation extractable.
Yeah,
I mean, maybe still with these caveats, but I think it's more like that. They actually, what is probably the reason is that these works rely on Fiat-Shamir. That is known. There are other works that, for example, in the case of Sigma protocols, show that Fiat-Shamir gives you something that gives you simulation soundness. So it's not a coincidence that they resist to these attacks.
I see.
But unfortunately, what maybe is the fact that like just Fiat-Shamir does not. I mean, what we have shown, for example, is that Fiat-Shamir does not give you simulation soundness or extractability for free in the case of these schemes.
Makes sense. Makes complete sense. Thank you very much for your answers, and I think we can wrap it up here. So thank you very much, and we're really grateful that you came and did this really good explanation, at least to my perspective, of course. Thank you very much, and you're welcome to come any other time you want.
Yeah, thanks to you for hosting me.